Have you ever wondered how engineers can predict the exact motion of something like an engine's piston using pure math? Well, that's exactly what we're going to tackle today. We're going to dive deep into the slider crank mechanism and build the mathematical model from the ground up, step by step, so we can pinpoint the precise position of every single part. So, here's our game plan. First, we'll talk about why we even need this kind of analysis. Then, we'll walk through the core derivation of the equations. After that, we'll apply it all to a real-world example and even see how it's used in some simple code. By the time we're done, you'll be able to build and solve these kinematic equations all on your own.
Okay, so the slider crank. It is everywhere. You'll find it in car engines, manufacturing equipment, you name it. It's what we call an RRRP mechanism. And that just stands for its joints, 3 revolute, or rotating joints, and 1 prismatic, or sliding joint. Now sure, we could try to just sketch its motion, but for modern engineering, that's just not precise enough. So here's our puzzle. If we know the length of each link and the angle of the input crank, can we figure out the exact position of that slider and the angle of the connecting rod or coupler? Let's find out.
All right, let's get into the heart of the challenge, how we actually solve this thing with mathematics.
The key to solving this whole thing is something called the vector loop closure equation. Think of it like this. There are 2 ways to get from that fixed pivot point A star to point B on the slider. We can go along the crank, vector R2, and then along the coupler, vector R3. Or we could take a different path, go along the slider's path, R1, and then up by the offset, R4. Now, since both paths end up in the exact same spot, they have to be equal. This simple idea gives us our fundamental equation, R2 plus R3 equals R1 plus R4. And here's a really crucial detail, that R1 vector, the slider's position, that is the only length that changes as the crank rotates.
Now, a single vector equation is pretty tough to solve directly, so we're going to break it down. We'll split each of those vectors into its horizontal or x component and its vertical or y component. This one move transforms our one vector equation into 2 separate scalar equations. So now we have a system with our 2 unknowns, r1 and θ3, all mixed together. The next step is to figure out how to untangle them.
So we have our 2 equations, but our 2 unknowns are still tangled up in there. Let's start the algebraic magic to isolate them.
To solve for one unknown, we first need to get rid of the other one. Our strategy is pretty straightforward. We're going to eliminate θ3 so we can find the slider's position, R1. The first move is to just shuffle both equations around a bit, getting all the terms that have θ3 in them on one side, all by themselves.
And here comes the really clever part. This is the key move. We take both of our rearranged equations, we square them, and then we add them together. Now, why on earth would we do that? Well, because on the left side, we get a term that looks like r3 cosine θ3 squared plus r3 sine θ3 squared. And thanks to the Pythagorean identity, that whole big expression simplifies down to just r3 squared. And just like that, poof, our unknown angle, θ3, has completely vanished. We're now left with one big equation that only has one single unknown, r1.
You know, after all that complex algebra, you might expect a really messy result. But when we group all the terms together, something pretty amazing happens. It simplifies perfectly into a standard quadratic equation for r1. It's just r1 squared plus a times r1 plus b equals 0. And the best part is, those coefficients, a and b, they're just combinations of things we already know, the link lengths and that input angle.
So, solving this quadratic equation gives us 2 possible answers for R1, and that's because of that plus or minus in the formula. This isn't some kind of math error. It actually represents 2 real physical possibilities. As you can see in the diagram, for the very same crank angle, the coupler can be either up or down. We call these the 2 assembly modes. We use that sigma variable to just pick which one we want to analyze. Oh, and if that number under the square root ever becomes negative, it just means the parts are too short to connect. The mechanism simply can't be built in that position.
Okay, now that we've found r1, we can circle back to find our last unknown, θ3. We just plug our value for r1 back into our earlier equations, and then divide the sine equation by the cosine equation to get the tangent of θ3. But here's a super common trap. If we just use a standard arctan function, our calculator won't know if the angle should be, say, in the top right quadrant or the bottom left. That's why we must use the 2-argument function, atan2. It looks at the signs of both the numerator and the denominator, so it always gives us the angle in the correct quadrant. No ambiguity.
That's all the theory. Now let's put these equations to the test with a concrete example and see how they work. Let's take a look at example 7.4. We've got a simple inline slider crank here.
The crank is 5 inches, the coupler is 8 inches, and the input angle is 45 degrees. Now, since it's in line, that means the slider offset is 0, which is going to make our A and B coefficients a lot simpler to calculate. Our goal is to find the slider position R1 and the coupler angle θ3 for the positive assembly mode.
Okay, let's plug in the numbers. Since our offset R4 is 0, calculating A and B becomes way easier. The B coefficient is just R2 squared minus R3 squared, which gives us negative 39. The A coefficient simplifies down to negative 2 times R2 times the cosine of our 45-degree input angle, which works out to be negative 7.071. So now we've got our A and B. We plug them into the quadratic formula, and we choose the positive root for our assembly mode. Solving that gives us a slider position R1 of 10.712 inches. And finally, we take this R1 value and use it in our A tan 2 formula to find that coupler angle. The result, negative 26.228 degrees. And there we have it, the exact position and orientation of our mechanism.
So why do we go through all this trouble? Because this analytical solution is absolutely perfect for computers. We can translate our equations directly into a script like this one here in Python. And instead of solving for just one angle, we can now analyze the mechanism's position at thousands of different points in a fraction of a second. This is the real power of analytical kinematics. It lets us do rapid, precise, and repeatable analysis that would be totally impossible to do by hand.
So let's wrap all this up and see where this analysis is going to take us next. So we've successfully taken a physical mechanism and turned it into a set of equations that a computer can solve in an instant. That is the foundation of modern mechanism design. But knowing where things are is only half the story. The really interesting questions are, how fast is that piston moving, and what are the acceleration forces acting on it? To answer that, we're going to need to take the derivative of our position equations with respect to time. And that's exactly what we'll do next time as we move from position analysis to velocity and acceleration.